Good morning, my name is Simon Klemperer, and Mary Leach has asked me to give you this introductory lecture on the geophysical techniques that we find useful to learn about and understand global tectonics. The theory of plate tectonics tells us that the outer layer of the Earth can be divided into a number of nearly rigid plates that move past each other or with respect to each other across transform boundaries, such as the San Andreas Fault, across convergent subduction zone boundaries that define the ring of fire around much of the Pacific plate, and moving apart from each other across ocean ridges, extensional boundaries. The number of plates, the definition of plates, is actually a little hard to get a handle on. You'll see, for example, that this graphic shows the Indian plate as separate from the Australian plate. Let's look, though, at just one of the techniques we might want to use to define the different plates of plate tectonics. Seismicity. This map has one yellow dot for every earthquake, magnitude 4.5 or larger. This map shows you the distribution of seismicity, that's the global distribution of earthquakes, over a 15-year period, with one yellow dot for every earthquake of moderate or larger size, magnitude greater than 4.5. Over much of the Earth, that seismicity is enough to define the plate boundaries, the Mid-Atlantic Ridge, the Pacific Ring of Fire. And you'll notice that much of the Indo-Australian plate boundary is similarly defined. But there's very little seismicity in this region where the previous graphic broke the Indian and Australian plate into two. Clearly, therefore, seismicity will be one geophysical technique we'll use to study global tectonics, but we need others in order to understand the full range of tectonic styles. We also need to look deep within the Earth if we want to understand the way in which subduction of oceanic plates beneath the continents is the major engine that drives mountain building, that drives orogenesis and deformation of the continents and the plates themselves. Let's talk about some of the geophysical techniques we might use to study global tectonics. We've mentioned seismicity, characterizing the location and type of earthquakes as a way to recognize plate boundaries. We might use satellite geodesy to look at the relative motions of modern plates. But if we want to look back into the past, we may need to use paleomagnetism to figure out how plates have moved past each other. And then we want to look deeper in the Earth. We can use what we call structural seismology, looking at the way the waves from distant earthquakes interact with structural boundaries beneath our feet. If we're using distant earthquakes, teleseismic earthquakes, we call that passive seismology. If we're creating our own miniature sources of seismic energy, controlled sources, whether it's dynamite or vibrators or air guns, we'll call that active seismology. In addition, there are complementary techniques, heat flow, electromagnetism, gravity, that can be useful in various situations. Let's go back to seismicity. What can we measure about earthquakes? We can locate where the earthquake is, we can define how far below the surface it is, and the hypercentral location, of course, captures both those, the location in 3 dimensions. The earthquakes tell us where the Earth is breaking, hence the brittle part of the plate. Most earthquakes happen in the top 20 kilometers of the Earth, except in subduction zones where they travel down, go as deep as the transition zone, about 670 kilometers. And this graphic just captures some of the things we can learn about earthquakes. We can recognize where the earthquake is. We can recognize the different sorts of waves that may travel from earthquakes, P and S waves traveling relatively fast from a close-by station to a close-by station, or taking a longer time to arrive at a more distant station. Traditionally, the recordings were made with a pen on a paper chart, and we could see the quiet trace here, the P wave arrives. After some later time, the S wave arrives, and then what's often the largest waves, most destructive waves, the surface waves. We can use all of these to help locate the earthquakes and also to understand something about the nature of the earthquakes. Locating earthquakes can be as simple as triangulation. If we have three different recordings of a single earthquake, here we line up the recordings from, in this case, Denver, and we recognize the time delay between the P and the S arrival. We have a recording at St. John's, Newfoundland, and again we see a characteristic time delay between the P and the S arrival. And finally a recording from South America, and again a delay between the P and S arrival. We know roughly the velocity of P waves within the Earth, the velocity of S waves within the Earth, and so the distance, the interval between the arriving P and S waves tells us something about the distance the waves have travelled from the earthquake. The 3-minute interval lets us draw a circle of radius 2,000 kilometres around Denver. This 8-minute interval, measured at St. John's, defines a circle of radius about 5,000 kilometres. And the 12-minute interval seen at Lima defines a circle of radius 9,000 kilometres. Where these circles intercept is the epicenter or location of the earthquake. Obviously we do this in 3 dimensions. We don't use just the P and S waves, but other phases if we can recognize them. The second important thing we can do is look at the sort of earthquake by looking at the first motion of the earthquake. If the recording shows the first motion is an up or compressional direction, that tells us that we are located with respect to the earthquake such that the first waves were travelling towards us, and the part of the Earth on that side of the fault was travelling towards us. If the first motion was down, then the Earth was pulled away from us at the beginning of the earthquake. We can map these first motions at different locations around the Earth and use that to identify what sort of earthquake. We can use these measurements of first motion on recording stations around the Earth to recognize the geometry of faulting using the so-called focal sphere. Here, in the view from the side, imagine the location of the earthquake fault and a hemisphere drawn beneath the surface. Here's the view from above. We see the hemisphere as a circle. Imagine rays or seismic waves leaving the earthquake and travelling to the far side of the Earth. If these rays have a compressional or up first motion, we'll shade them white in this case, and we'll plot them on the focal sphere all the earthquakes that recorded compressional first motion. Looking down from above, in this case, that will be this central region of the beach ball. Stations close by will record rays that will leave like this and like this, and may record tensional, extensional, dilatational first motion, down in this example. And we're going to shade those grey, and those produce the areas around the margins of the beach ball in this example. So we build up a picture showing which areas of the focal sphere were extensional, which areas were compressional. And we find characteristic patterns for the beach balls depending on the type of earthquake. For the normal fault or extensional fault, we see a beach ball with compressional patterns in the centre and extensional patterns on the margins. The reverse fault or thrust fault has the opposite pattern, where now we have compressional patterns on the margins and extensional patterns in the centre. Strike-slip faults will have their own characteristic pattern, in this case for a vertical strike-slip fault, across. This gives you a sense of the way in which we can recognize for each earthquake whether it represents an extensional or compressional event. We can also measure how large an earthquake is. At its simplest, that will be how large are the amplitudes of the seismic waves when we record them on our pen drawing on paper, and that was the way the Richter-Gutenberg amplitude was first defined. That works well for local earthquakes. For more distant earthquakes, we might want to use the surface waves, or, even better, a measure based not on amplitude, but the amount of energy released by the earthquake moment. How far the fault slipped, and how large was the fault area that slipped. And that's regarded as the best earthquake magnitude to use. Particularly at the largest magnitudes, it gives somewhat different results from the Richter scale. For example, we can talk about one very large earthquake that happened a few years ago, the Sumatra earthquake before Christmas in 2004, that killed 250,000 people around the coasts of the Indian Ocean due to tsunamis. The earthquake was located on the subduction zone beneath northern Indonesia and was a large low-angle thrust fault. From the earthquake, from the USGS Earthquake Center, we have basic information. We have a magnitude, we have a time, we have a location, we have a depth. In the first few hours after the earthquake, automated recording at stations around the globe produced this focal mechanism that showed the extensional quadrant and the compressional quadrant on the margins. This was a thrust fault, and the active fault was this very low angle fault, dipping about 8 degrees, striking northeast, parallel to the subduction zone. These automated solutions give us the first most basic information, but in this case, this large earthquake only gives us the most broadest brush information about this subduction zone. In fact, the detailed tectonics are far more complex. These graphics from papers in preparation before the earthquake, published soon after it, show how the subduction zone on which the earthquake happened is overlain by a region dominated by transform faulting that is then producing mid-ocean ridge spreading in pull-aparts in the upper plate. Here in more detail on the right. We're going to need to use all the aftershocks and indeed far more information to understand the details of the tectonics around this area. The 2004 earthquake broke an area hundreds of kilometers long on the northern Sumatra subduction zone. We can look back further in the record using evidence from uplifted coral beaches and find that 150 years ago another 100-kilometer segment broke further south, and 150 and 250 years ago yet another segment. No seismicity has been recorded in the northern part of the Indian Ocean, where the same subduction zone extends northwards into Bangladesh and beneath Burma. And so this area is now the one that people have great concern for in terms of future seismicity. But it shows the limitations of using modern seismicity to study tectonics, in that the historical seismic record is less than 200 years old. Seismicity can't give useful plate convergence rates because we only have rare large earthquakes. We don't know when the earthquake preceding the 2004 event was that was similar in size. We don't know how often they occur, and so we can't calculate the plate convergence rate. We have to turn to other techniques. Over multi-million year timescales, the method of choice is going to be paleomagnetically determined locations. First we build a geomagnetic timescale by dating rocks to get their ages and measuring their magnetic polarity to determine whether they're normal polarity, that is, the same polarity as Earth at present, or whether they're reversed polarity. For the last 750,000 years, Earth's magnetic field has had the same polarity as it does right now. But if we go back to 1 million years, we would find that the polarity was reversed. And the polarity of the Earth's dynamo has flipped at shorter and faster rates throughout geological history. These geomagnetic reversals are best exemplified with the seafloor magnetic stripes that were one of the first strong pieces of evidence in favour of continental drift and plate tectonics. If one measures the polarity of magnetism on the sea floor, one finds a series of stripes parallel to the mid-ocean ridge, and ideally symmetric around it on both sides. Our model is that of a magnetic tape recorder. As magma rises to the surface of the mid-ocean ridge and the ocean crust forms with the plates spreading apart, magma formed at the present day is formed with normal polarity, positive polarity. Magma formed 1 million years ago has negative polarity because at that time the Earth's magnetic field was reversed. And so on into older and older crust as we move away from the ocean ridge. Once we've developed a magnetic timescale in one part of the ocean floor, we can then very quickly calculate the age and spreading rates for seafloor elsewhere on Earth by measuring the magnetic signature. This is done very quickly from a ship towing a magnetometer. The oldest ocean crust on Earth is 160 million years old, and so for the last 160 million years we have a very detailed record of magnetic anomalies, and during this period of Earth's history we're able to assess plate motions very precisely. We can figure out the paths of each individual tectonic plate relative to each other and the location of those plates on the globe for the last 160 million years. As we go further back in time, the record becomes harder and harder to decipher. The oldest ocean crust, 160 million years, offshore Japan, perhaps in parts of the westernmost Atlantic or Gulf of Mexico, lets us recognize plate motions at those times. When we go further back in history, we need to use the paleomagnetism of continental rocks. That magnetism is measured by drilling cores, oriented cores of rock, and then in the lab measuring their remnant magnetism. The orientation of that magnetism relative to the present day orientation of the magnetic field tells us something about the paleolatitude and rotation of the crustal blocks in the intervening millions of years since the magnetism was formed. There are different ways in which this magnetism can be preserved, whether it's a thermal magnetism, a depositional magnetism in sedimentary rocks, or a chemical magnetism. And so any one individual measurement can be subject to multiple interpretations. Furthermore, if there are very many small plates present on Earth, then it can be very hard to decipher the relative motion of all those plates. At time periods, even in the Mesozoic or in the Paleozoic, when the plates were widely dispersed, there may be large uncertainties in where those plates are, whereas at times where we had supercontinents, there may be a much smaller uncertainty in the plate motion. As we go back in time, that uncertainty tends to increase. Increasing numbers of measurements across the whole Earth means that it's now possible to make some sort of estimates of continental dispersion and continental locations back even into the Precambrian. For recent times, that is the last 2 or 3 million years, we use a combination of paleomagnetism of the oceans and satellite geodesy. Some of the models that are most well known are Nouvelle 1A, a model that's 20 years old now, that's based entirely on those plate motions. It's an average over the last 3 million years. Another estimation, an update of the older model, also looks at hotspot motions and assumes that by and large they remain fixed with respect to each other. HS3 Nouvelle 1A includes hotspots as well as marine magnetic anomalies over the last 6 million years. And this map shows relative plate motions at the present day, or averaged over those last few million years, based on those models. We also now have access to geodetic data and space-based global positioning system data. And the model Revel 2000 is based entirely on space-based geodesy. Some plates, like the Scotia Arc, are very poorly determined. They may have no land masses on them. Other plates are very well determined. This model only averages over the last 10 to 20 years. Nonetheless, this model is very compatible with the average over the last 3 million years from Nouvelle 1A, and shows that by and large, space-based geodesy is capturing the average values over the last few million years. The orange arrows and the blue arrows agree very well, except for the slowest moving plates, such as North America, where there are substantial disagreements because the rates in direction, because the rates, absolute rates, are so slow. It's important to recognize that geologic reconstructions and geodesy may be at odds. To take a couple of examples from Southern California, we find that geodetic rates and geologic rates may differ by factors of 2 even in the last million years. In the Western Garlock Fault, the geodetic rate is half the geologic rate. In the Eastern California Shear Zone, the rate is twice the geologic rate. Presumably, the number of earthquakes, we haven't seen complete earthquake cycles even over this million-year timescale in order to properly capture the long-term average motion on these faults and for these small-scale crustal blocks. We've talked about seismicity to characterize the source, to locate earthquakes, to look at the fault type, to analyze the plate boundaries. Now we want to talk about using seismic methods to image the crust and the upper mantle. We're going to use the way the crust and the mantle perturb the rays, those seismic waves traveling through them, using either active methods, in which we will create our own controlled sources, and passive methods using distant earthquakes. We've already talked about the way seismic waves propagate through the earth from an earthquake. And in this graphic, we see schematically the ray paths that are taken from an earthquake in Southern California to close by stations, to more distant stations, to yet more distant stations. The close-in stations only see rays that travel through the shallow parts of the earth. The far stations see rays that travel through the central part of the earth, even through the core. At close distances, we see the P waves and the S waves are close together, and they gradually get more and more separated as we move to longer and longer times. That's the method we use to locate earthquakes. To a good approximation, the Earth is spherically symmetric, and we can see this by stacking together the seismic energy from many different earthquakes. In this example, 33,000 separate seismograms have been stacked. We normally record earthquakes on sensors with 3 different components recording: a vertical, a north-south, and an east-west. 3 components of motion capturing the entire vector wavefield. When we stack all the vertical components for these 33,000 seismograms from 0 to 180 degrees, that's the far side of the Earth, and plot the travel times from 0 to 60 minutes, 1 hour, we see a very well-formed pattern, again with the P waves, with the S waves, with the surface waves. The fact that all these seismograms from many different earthquakes around the Earth all have the same arrival times at the same distance shows us that to a first approximation the Earth is spherically symmetric. And this arrival time information has been used over the last 100 years or so to develop the symmetric model of the Earth. The inner half of the Earth's diameter is made up of the core, a solid inner core, a fluid outer core, which convects and produces the Earth's dynamo. The outer half of the Earth is the mantle, which we divide into a lower mantle and above about 670 kilometers, an upper mantle. The upper mantle and the lithosphere above it, the crust, are what allow the plate tectonics to take place on Earth. If we look at seismic wave speed with depth down to the core, we can see a gradual increase in seismic wave speed or velocity through the upper mantle, and then in the liquid inner core a big drop in the P wave speed and no S wave propagation at all, and then an increase in the inner core. In the shallow levels of the Earth, the top 100 kilometers or so of the crust and the lithosphere, we see much more rapid changes in the Earth's structure and the geometry of the plates. This is most dramatic when we look at subduction zones, and we can map the change in seismic velocities across a subduction zone. Here, the colors represent seismic velocity. High velocities in blue map out a subduction zone. Low velocities in red map out low velocity rock. Most of the upper mantle has a very uniform composition, so changes in velocity represent changes in temperature. Blue is cold, red is hot. We call this sort of image a tomogram. We use body wave tomography, the same scientific method as the ultrasound tomography that images a baby in a mother's womb. To take an example of how this works, suppose I have an anomalous object, maybe a high velocity body beneath the Earth's surface. Suppose seismic waves travel through it from a distant earthquake. Waves that miss the anomalous object will show up at a normal travel time. Waves that travel straight through the object will have a relative travel time delay or advance. Rays that miss the object will again have a normal travel time. Imagine seismic waves coming from an earthquake on the other side of the Earth. I can see the same pattern in a different place. This seismic station now sees a normal Earth. This seismic station sees the main effect of the body. This seismic station sees the normal pattern again. By back projecting these seismic travel time advances or delays and finding a single solution in the subsurface that can match these travel time anomalies on these stations from this earthquake with these travel anomalies on these stations on this earthquake, I can locate this high velocity body in the subsurface. That's the essential principle of tomography. Tomographic images show us large-scale variations in the seismic wave speed or seismic velocity deep beneath the Earth's surface. This image is a horizontal slice through the Earth at 100 kilometers depth beneath the US. The most dramatic feature on this image is the boundary between the western US, that is red or hot, and the eastern US, that is blue or cold. This boundary is far more important than any difference between ocean crust and lithosphere and continental crust and lithosphere. It's the temperature of the mantle that makes the biggest difference in these velocities. And so now we have a seismic proxy for temperature. Temperature, of course, controls the viscosity of the mantle, allows the mantle to convect, allows the mantle to move and drive plate motion at the surface. The same contrast between western and eastern US that we can see in mantle seismic wave speed is also present when we try and measure the heat flow at the Earth's surface. In the western US, we see these red patterns, very high heat flow, maybe 100, even 150 milliwatts per meter squared. In the eastern US, we see these green and blue patterns representing only 40 to 60 milliwatts per meter squared. That contrast between the western and the eastern US is what causes the western US to have such active tectonics and the eastern US to be old and cold, rigid and resistant to tectonism at the present day. If we look at the very largest scale, global heat flow out at scales of thousands of kilometers, we see the highest heat flow developed over the mid-ocean ridges, the East Pacific Rise, the Atlantic Ridge, the Indian Ocean ridges. The coldest parts of Earth are the old cratons. Here, West Africa, South Africa, to some extent, Southeast US, and in Siberia. So global heat flow is a good proxy for modern tectonics, tectonic activity, and can be measured by seismic tomography. Here, looking at cross-sections through the Earth on the top slice, and looking at depth slices, that is, spherical sections at different depths in the mid-upper mantle, all the way down to the core mantle boundary, we can see there are very large-scale features in the mantle that help to drive tectonics at the surface. The feature called the Africa Superplume is a region of extremely low velocities. The low velocities can be tracked from the core mantle boundary in southernmost Africa and rise along a slanting region up towards the Gulf of Aden and the Afar hotspot at the surface. We think that heat flow out of the core is heating a region in the lower mantle that then rises as a plume and drives tectonics that we can see at the surface today. One additional twist to measuring the seismic velocities is that these wave speeds are not the same in all directions. Just as we use optical petrography to look at different mineral types, and we use the birefringence colours to distinguish minerals, that principle depends on light travelling at different speeds in different directions in anisotropic minerals. So we can look at the different velocities of seismic waves in different directions. These images show a measure of how anisotropic the Earth is at different depths, and it shows regions where the horizontal direction is fastest, shown in blue. These are regions where the mantle may be spreading sideways, and in the upper mantle will be due to mid-ocean ridge spreading. In contrast, we see some regions where the vertical direction is fastest. These are regions of rapid downwelling and are characterized particularly along subduction zones of the Pacific margins. We'll see shortly that we can use this anisotropy to look in much more detail at the structure of the continents. As a seismic wave propagates through anisotropic medium, it becomes split into two waves. A slow wave shown here and a fast wave shown here. As the wave emerges from that anisotropic medium, the fast wave will lead, the slow wave will lag, and we can measure a travel time, a degree of splitting of this waveform. That degree of splitting is proportional to the amount of anisotropy in the anisotropic medium and the length of the wave path within this medium. We can measure both the direction and the amount of anisotropy at the Earth's surface. We call this measurement a measure of shear wave splitting. This map shows measures of splitting at different seismic stations around the Earth. Over broad regions we get more or less consistent anomalies that we can relate to local tectonics. In much of the basin range of North America we can see splits that are parallel to the spreading direction, just as we see across ocean ridges. In other areas we see much more complex patterns. In Tibet we see split directions that are perpendicular to the compression between India and Tibet. And there remains some debate in the community whether these splitting directions represent a asthenospheric flow in which the splitting is taking place in the asthenosphere. Asthenospheric motion is driving plate motion, and so the split directions are proxies for absolute plate motion. And other places, particularly in active tectonics, where vertically coherent deformation may be taking place, if, for example, we are compressing Tibet between India and Asia, we're squeezing these rocks together and we're developing a fabric that will, in this case, have a fast direction perpendicular to compression. Both sorts of behavior appear to be present on Earth, and we can use our mapping of these split directions to unravel some of the complexities of active tectonics. There are many other methods used with modern broadband seismology for interpreting structure. One that yields some of the most dramatic images of the Earth is called the receiver function method. When a seismic wave from an earthquake comes up from deep in the mantle up to a recorder, it produces a direct pulse. But the same wave may also convert from a P wave to a shear wave at any boundary, like the moho, and this gives rise to a second pulse. We can have what we call multiple events, where a wave will come up, bounce down, bounce back up to the surface, and these multiples will confuse our image. But the principle is that we will have direct P waves and we'll have delayed waves due to the S conversions. By forming an image of these converted phases, we can produce an image of the converters in the subsurface, the boundaries, such as the moho, where these conversions take place. Here's a series of seismic waveforms in which receiver functions have been calculated, and from the surface, shown here, we see a clear arrival in the receiver function at a depth of about 30 to 35 kilometers that very clearly marks the moho, in this case beneath southern Africa. We can look to any depth by using lower frequencies here in the southwest USA. Instead of looking down 30 kilometers, we can look down 300 or 400 kilometers to see converters at the mantle transition zone at 400 and 670 kilometers, the boundary between the upper mantle and the lower mantle. Some of the most dramatic images come from subduction zones. Here we're looking at an image collected across southern Oregon, in which we see very clear conversions beneath the continent. This section runs from west to east, across the coastline, and it spans about 250 kilometers. On shore, we can see clear boundary at the continental moho. Red is low velocities above blue high velocities. We can see the oceanic crust subducting this red layer into the mantle. We can see in the oceanic and arc part of the crust, we see a mafic lower crust that is actually higher velocity than a serpentinized mantle. The mantle here has reduced velocity because of water coming off the subducting ocean crust. And at greater depths, we see a range of apparent seismic phases that are actually multiples, are misaligned energy. One needs to be cautious in interpreting any of these images. But the main features are clear, the moho and the subduction zone. This receiver function technique is very analogous to the seismic reflection technique of active seismology. In the reflection technique, we use sources of seismic energy at the surface. The energy travels down, reflects off a boundary, and back to the surface. The difference between reflection and refraction: in reflection, we think of ray paths that are near vertical, whereas in refraction, we think of ray paths that travel a much longer distance horizontally than they do vertically. Here we see that comparison. Vertical reflection data typically has source to receiver offsets less than 10 kilometers, but images reflectors may be faults, or the moho down to 30 or 50 kilometers. This is much deeper than even the deepest well that has yet been drilled on Earth. In contrast, refraction or wide-angle seismic data, the sources are used to drive seismic energy to much longer offsets, several hundred kilometers, but these rays penetrate a much smaller relative distance into the Earth. Reflection seismology is used to provide echo times, and then, if we know velocities, depths to structure. Refraction seismology is used to measure the velocities that we need to convert reflection echo times into depths. Here's one of the more dramatic reflection images that has been collected, an image across northwestern Canada. This section is about true scale. It goes down 100 kilometers into the Earth, and so spans 500 kilometers from west to east. It's really very easy to see the moho, the base of the crust on these sections, and in this case to see a fossil subduction zone where oceanic crust was subducted at the same time as thrusting was developed on the western margin of the Watmay origin 2 billion years ago. In this case, frozen into the crustal structure, we see old thrust faults and underthrust subduction zones beneath the moho, preserved for 2 billion years. The cartoon below shows the interpretation of these data. Refraction data are much harder to read directly from the image. In this case, we see a plot that is a function of the travel time of the data, plot against offset out to 250 kilometers. By convention, refraction seismologists have time increasing downwards. We see the first arrival, the energy from the shot can arrive at different times, at different offsets. We guess a model of the Earth's crust in depth, and we guess the velocities down to different horizons. We trace seismic rays or seismic waves through the structure that we have guessed, and we calculate the travel time of these rays. We adjust our model until we successfully fit the arrivals that we see on our data. And then we believe our model is a reasonable approximation of the Earth. Our seismic velocity model, again, spanning 200 or 300 kilometers would be typical, showing in red very low sedimentary velocities at the surface, velocities of 5.5 to 6 kilometers a second may be a granitic crust. Velocities increase 6.5, 7 kilometers per second down to a major jump at the Moho. And in this example, across the California-Nevada border in the Northwest Basin Range, measuring the crustal thickness and how it changes, identifying this relic of the Sierra Nevada batholith were important conclusions from this study. At its best, active seismology combines reflection and refraction data. Here is reflection data across the San Andreas Fault, and the authors of this study were able to directly image reflections here from the San Andreas Fault. At the same time, the wide-angle data measured the velocity model. The colors here convert to velocities, and the boundary between the high velocities in red and the lower velocities in blue and yellow corresponds to the major faults. At the beginning of this lecture, I mentioned a few other geophysical techniques that can be useful, and so I'm going to show just one example of where magnetic, electrical, and gravity methods have allowed more detailed interpretations. In the last decade, university geologists and the US Geological Survey drilled a deep hole into the San Andreas Fault at Parkfield, where over the last 60 years there have been 3 magnitude 6+ earthquakes. The San Andreas Fault Observatory at depth, that drill hole was offset from the San Andreas Fault by about 1 kilometer, drilled down to 2 kilometers depth, then sideways through the San Andreas Fault to recover cores from the fault. A couple of slides earlier I showed you how hard it was for seismology to image the near vertical boundary of the San Andreas Fault. But electromagnetic data are an excellent way to image vertical fault zones. Vertical fault zones often trap fluids, and in this case the San Andreas Fault Zone turned out to have very low resistivity characteristic of saltwater or seawater present in the fault zone, whereas the surrounding rocks, the Selenian granites, have much higher resistivities, higher by 2 orders of magnitude. The best image of the fault zone comes in this case from electromagnetic or magnetotelluric profiling. At the same site, US Geological Survey scientists combined multiple methods. They used aeromagnetic data, that is, flying an aeroplane at low altitude to measure the magnetism, ranging from very low over the San Andreas Fault to higher over the granites to the southwest. Measuring gravity, how strong is the Earth's pull, lower over sedimentary rocks of the Great Valley, higher in this case over the granites, and compared this in great detail to the geological mapping in various transects across the San Andreas Fault. Using the geology to decide the surface densities to estimate gravity and the surface magnetism to understand the aeromagnetic image, they were able to model the geology at depth down to about 10 kilometers here across the San Andreas Fault as different sorts of basement and granites, and then Great Valley sediments on the northeast side of the fault. Integrating multiple methods gives a much more reliable solution than any one method on its own. Gravity anomalies at a larger scale do map crustal structures. For example, on this gravity map of the United States, we can see some of the principal features. We can see low densities, low gravity in blue over the Sierra Nevada batholith, where the granites extending to 20 or even 30 kilometers depth are lower density than surrounding rocks. And we can see some very high density regions. For example, the mid-continent rift, a region of intrusion of very dense mafic rocks 1.6 billion years ago. We see a similar high density zone beneath the Atlantic states, probably related to magmatic intrusions during Atlantic rifting 150 million years ago. In this way, we can compare the signatures of active tectonics with the signatures of older parts of the continents and help us to understand the tectonics long extinct in those parts. In the oceans, gravity is even more revealing and can be measured even more simply using satellites. If a satellite passes over the surface of the Earth, its orbit is affected by the strength of the gravity field beneath it, and it can also measure exactly how high it is by looking at reflections from the sea surface. If gravity was uniform, the sea surface would be flat, apart from waves, of course. Where we have high densities beneath the seafloor, ocean is attracted to that high density and sea level is higher. The satellite can measure how high that sea level is and then convert that into a gravity map of all of the Earth's oceans. And that gravity map, developed by Sandwell and Smith, is a remarkable tool for looking at the tectonics of the oceans. It's extremely clear to see the very large gravity anomalies associated with subduction zones, telling us that we have very large subsurface anomalies where dense cold ocean crust is subducted beneath the continents, beneath the continental margins. We see some signature from the Hawaiian Emperor Seamount chain, a rather local signature due to the loading of the hotspot volcanoes upon the oceans. Perhaps what's most remarkable is that in a place like the East Pacific Rise, we really see no localized anomaly. We see very long wavelength changes in gravity, showing us that the ocean ridge spreading is driven by very long wavelength upwellings in the mantle. Thus, the marine gravity, which is really a map of the satellite altimetry, is one more tool for looking at active tectonics of the oceans.